Okay. Okay, so we discussed branch target buffer. So using the branch target buffer, the fetch stage, we can predict the address of the next instruction, which is the target instruction. Target address. 한효정 stack top. So you send your program counter, and then you can search this table, which is BTB. And if you hit in this table, then it means it's a branch instruction because you record the address of the instruction before, right? You only store the address of the branch instruction in this table. Okay? So once you hit the BTB, you have to check the condition if this is a conditional branch. So about 80% of the branch instructions are conditional branch instructions. Okay? So using this branch condition prediction, you can predict condition. They use, for the original BTB, they use 2-bit bimodal predictors. 2-bit bimodal predictors. So they look at the MSB, the high bit, the high order bit, most significant bit of this 2-bit counter. And if this is 1, then you predict it taken, as taken. If it's 0, then you predict not taken. That's based on this state machine. So it can start from 0, 0, right? So initially, the table contents will be empty. So once you perform the branch instruction, once you execute the instruction, you insert instruction address, and also you also look at the condition. If the condition was taken, then you increment the counter. Condition is not taken, you decrement the counter. It's simple, right? You increment or decrement. So most of the time, if it's taken, then it will be set to 1, 1 or 1, 0. Okay? Then you predict it as taken because MSB tells you it's taken, right? 1 means taken. If it's 0, 0 or 0, 1, you predict as not taken because most of the time it was not taken before because the state says it's 0, 0 or 0, 1. Okay? So by looking at the MSB tells you the history of the branch execution before. And 1, 0 or 1, 1 means most of the time it was taken before. So you predict as taken. If the state was 0, 0 or 0, 1, then it was decremented before, right? So it means it was not taken frequently, so you predict not taken. Okay? So once you hit the BTB, if the condition field, bimodal predictor, says it's taken, then you look at the target, right? Target for direct branch, as I said. For example, in the MIPS architecture, most of the branch instruction, you encode the target address in the branch instruction. Right? In the instruction, hard-coded. So it does not change, right? If you go back to the loop, it's going to the loop again and again. If you're going to some target, you're going to the target again and again, right? So if you store the target address, then it gives you 100% accuracy for this direct branch. What is indirect branch? 효정, what is indirect branch? Address can change anytime, right? Because the example is return instruction, jump register and return address register. Based on the content of this register, you can go back to any call site. Okay, because you put this return address in this register whenever you call this function. So you can go back to any call site depending on the jump locations, right? So in this case, these are called indirect branch because based on this register content, you can jump to anywhere. For this indirect branch, it's hard to predict using BTB, right? But for direct branch, which is the most case, right? You can predict accurately using the BTB. And this branch target buffer is used for most of the commercial microprocessors to predict the branch. Okay? And so, as I said, indirect branch is a problem, right? Indirect branch is a problem, but for return instruction, you can predict accurately. And it said it is called return stack buffer. You push return address on this buffer on a function call or procedure call, and you pop the stack on a return. Then you can predict correctly. Okay? The idea is whenever you use jump and link function call or procedure call, you're jumping to some function, right? And you usually store the return address to the return address register by the jump and link instruction, right? But at the same time, by the hardware, whenever you meet jump and link instruction, you put this return address on the stack, called this return stack buffer, or it's also called return address stack, depending on the processor, RSB or return address buffer. So it's a stack. So if say main called A called B, B called C, C called C recursively, then let's say the return address at the main function is called main dash and A dash and so on. Then whenever you call A, you have to put main dash, right? A dash, B dash, C dash, C dash and so on. Right? You put this return address on this stack, RSB. Whenever you return, the top tells you the call side, right? Stack top tells you you have to go back to this location. So you can pop the RSB. Then you can go back to the call side, even without looking at this return address register, right? So this is called RSB. No, you can understand, right? It's a stack. Simply you follow the call chain, right? And you, so by looking at the PC, all these return instruction addresses are stored in some other buffer called return address, maybe table or something like that, whatever. Then using the PC, if you match this instruction, because this table stored only the return address instruction, you can determine this is a return instruction. If this is a return instruction, you pop the RSB, then it tells you the return address, even before you execute this return instruction. In that way, you can predict also for return instruction, which is an indirect branch. Right? Understood? Hmm? So, in the fetch stage, you have program counter going into the instruction cache that gives you instruction. It also goes into the BTB and it tells you the target address, which is the address of the next instruction at the next cycle, and it also goes into the RSB. RSB also gives you target address. Right? If it's return, RSB gives you target address by popping the RSB. Okay? Or if it's direct branch, you can use the BTB, and they can provide the target address. Okay? So next cycle, this address, target address is go back to this stage, and it can fetch the next instruction, next cycle, without stopping, as long as branch is correctly predicted. If there is a misprediction at the execution stage, then you have to flush the pipeline and start from the new target address, which is calculated at the execution stage. Okay, this is the branch prediction. Okay. For condition prediction, we can use several different schemes. So we have reviewed this bimodal predictor, which gives you about 93% accuracy. In general, 60% of conditional branches are taken. So there are more taken branch than not taken branch. Stacked up. Do you know why? Why there are more taken branch than not taken branch? Any idea? Bonus point, 5 points. Why there are more taken branch than not taken branch? Direct branch. It's taken or not taken is nothing to do with direct or indirect branch. Right? Conditional branch in mixed architecture, they only have branch equal or branch less than these relational operators. They are all direct branches. Right? Because you hard code is the target address. Okay?
In loops, you have to take many branches before you actually exit the loop.
That's right. So I'll give you 5 bonus points. If you think about this backward branch, which is a loop branch, right? So 100 iteration, which means 99 iteration is taken. 100 last time it's not taken. So if you consider this loop branch, there are more taken branch than not taken branch. Okay? Good. So send email to PA and CC to me. Okay? Okay, so I have another bonus point, so wait for second chance. So using this characteristics, you can, without doing any hardware, you can predict backward branch is mostly taken, forward branch not taken. This is simple, right? Backward branch, except the last iteration is taken, forward branch will be, you can assume just not taken. They don't know. Then it gives you about 69% hit rate. Okay? And this requires hardware, this without hardware. Compiler can insert this information in the instruction. Okay? This branch will be taken or not taken. Okay? And another idea is, instead of doing this, we can use profiling technique, which is a common technique used by the compiler. Profiling means compiler, they do the translation, which means translate high-level language programming statement into machine language instruction. At the same time, they can learn the program before they produce to look at their behavior. Okay? So using the sample data, before they produce the actual binary code, they learn the program. And then they look at the tendency of the branch, which means whether this branch will be taken or not taken, right? Using the sample profile data. And usually branch are biased, either taken or not taken, depending on the type of, on the branch instruction. So by looking at this tendency, they can measure this branch will be taken, this branch will be not taken, right? By learning with sample data. Using this sample data and profiling data, if you encode that branch condition information, taken, not taken information, then it can give you 92.5% accuracy, almost close to bimodal predictor, right? But this requires you should be able to encode this information in an instruction, which means the instruction set architecture where the machine language should support that feature. So for example, IA64, Intel 64-bit instruction set, their instructions the programmer or the compiler can encode this information. So there is a bit field, statically predict taken or not taken bit. So using that bit you can encode. And hardware, whenever they decode this instruction, using that bit they can determine if this will be taken or not taken based on this compiler provided information. Okay, it's called profiling. Okay, and profiling can be used as a safety net when the dynamic prediction structure needs to be warmed up, which means, as I said, these hardware predictors, you have to execute the program, right? You have to build your history. at the beginning of program execution, there is no history. So all the tables are empty. You cannot use hardware for prediction. In this case, you can use this compiler profiling or compiler directed branch prediction, which is called static prediction, because compiler is usually we call static time, static hardware runtime dynamic. Okay. So for IA64 or Itanium processors, they use both compiler provides this profiling information, and also they use this two-level adaptive training scheme, which is more complex, more sophisticated branch predictors. Okay, let's look at hardware predictors. For BTB, if you use a single bit last time predictor, okay, last time taken, you predict taken, then it can give you about 89% accuracy, because they usually are biased. If it was taken before, then it will be taken this time also. If you use 2-bit counter instead of single bit, you can improve this accuracy by 93%, and using two-level adaptive training scheme. Okay, I don't know where he is. Actually, he left Intel. Okay, so I left Intel and I joined UC So I went to other school. At the time, we have about 25 people in the microarchitecture team, about 30 people, and there are about 7 microarchitects, which are the designers. And my my supervisor was a chief microarchitect, which actually a design team leader of 600 designers, which was Indian, Harsharan. He had this mustache with bald hair. It looks like Harry Potter style spy. I thought he was quite old, and he was quite young. Actually, he's close to my age. Actually, at the time I was only about 32, 33, 34, and he's about that age. But he looked old. But he said he spent about 12 years for processor design, and he was tired. And anyhow, I come to academia, and they actually tried to persuade me to stay on this team. But after I left this design team, actually Seiyue and my supervisor, Hashi Sharampini and Ken Aurora, another good, smart microarchitect, all left this team. And finally this chip was delivered by different people, different microarchitects, actually. And Harsh said he wanted to build his own company because he spent about 14 years in designing this. He started from 486 or 386 until Itanium. So he spent too many time in this design, so he was tired and he wanted to do another company. And he earned about $25 million. Because that, at the time, rule of thumb is after you get a PhD, you go to Intel, you spend 5 years, you earn at least $1 million. Okay? Because of the stock growth, right? But that's the peak. That was the peak time, because 1990, that was the peak time. After year 2000, this IT bubbles collapsed and Intel, all stock price go down, except Apple or maybe Google's, right? New player, so they are exchanging. Anyhow, Seiyue also left Intel after I left this team. Okay, I'm not sure he went back to Taiwan or maybe. Okay, so he came up with 2 levels of table. Using this table, he can improve this condition prediction to about 97%. Okay, and it's more complex. And at the time, there is another company called Digital Equipment Corporation, which was building the fastest microprocessor in the world, which was called alpha processor, digital alpha processors. Digital alpha processors are always the target for Intel's high performance processor because they always show the best performance in the world. Okay, and there is a good designer called Scott McFarlane. Actually, he optimized his design. He removed unnecessary tables, columns, and simplify and modify a little bit, and he improved this structure to more than 97%, 98, 99% with much simpler structure. And then many other people work on this issue. And nowadays, it's more than 98 or 99%. And in our design team, we have Seiyue and another PhD student from Yale Pet who also majored in this branch predictor. So we have got good design team at the time. And okay, so that was the history of branch predictors. Okay, let me give you another bonus question. Okay, let's think about this bimodal predictor. So initially, you can reset this counters. You can start from 0, 0. Would you reset to 0, 0 or would you reset to different state? Among these 4 states, which state would you give you the best performance intuitively? So would you consider 0, 0, 0, 1, 1, 0 or 1, 1? What state would you initialize? The first come, first served. 5 bonus. Okay.
1, 0.
1, 0 because?
Like before you said the taken is more occur frequently.
Why not 1, 1?
Well, it says about 60%, so it's more closer.
Okay, so I'll give you 5 bonus points. Okay? So because there are more taken branches, instead of 0, 0, 0, 0, then you start predicting from not taken. It's better to predict taken. But if you set to 1, 1, for not taken branch, you need 2 incorrect prediction, right? So if it's 1, 0, then you can switch quickly. So I would rather reset to 1, 0 state for the initial state of this bimodal predictor. Okay? Okay, so let's go to today's processor, which is, most of them are superscalar processors. Superscalar processor means in your Galaxy S3 or iPhone 4 or iPhone 5, those are actually embedded processors. They are not like commercial processors used by personal computers. Right? Those are more optimized for smartphone. Smartphone is kind of embedded computers, but nowadays we call them as a new generation of computer. Right? Every 10 years we have a new generation. We start from the mainframe, and then who is the leader in the mainframe business? Which company? IBM. Okay, one of the biggest computer company. Okay, after IBM produced this mainframe in early 1960s, about 10 years or later, new style of computers emerged, which are called mini computers. Mini computers. Who are the leader? Who is the leader in this mini computer business? Digital Equipment Corporation. As I said, Digital Alpha, Digital, which actually go away. They disappeared. Digital Equipment Corporation is acquired by HP. Nowadays it belongs to HP. Anyhow, mini computer. And then about 10 years later, workstations and servers. Who is the leader? Sun Microsystem. Have you heard of Sun Microsystem? SPARC Station, SPARC processors. Sun Microsystem was the leader, who also disappeared. It's acquired by Oracle. Disappeared means this business is gone, right? Mini computer is gone, okay? Workstations almost gone. Still they use workstation, engineering workstation. And it's replaced by personal computers. Who is the leader in the personal computer business? Okay, who? PC, who is the leader? Microsoft and Intel. Okay? Intel made this IBM PC for the first time. And they think of this box business. They can build a computer. And they give CPU, which is the central brain of this computer, to the Intel. He gives this operating system, which is the central platform of the software, to Microsoft. And this Microsoft and Intel actually become larger than IBM, because this business grows far faster than this PC business. Actually, when I joined Intel, at the time I joined 1996, April 1st. So I started there, with this necktie, and my secretary says, no necktie for the necktie, so they don't like. Anyhow, at the time, stock price means its market value, total value of the company, okay? IBM was bigger, Intel is about this much, and there is Microsoft, and there is a Cisco. You know Cisco, computer network company, okay? Cisco. And I exit here and joined Usual Buying about 2.5 years. Intel stock growth like this. When I joined, it was about $60. When I left Intel, it was also about $60, but there is a 3 stock split, which means it's 8 times expansion. Okay, that's the golden era for Intel from late 1980s to late 1990s. About 10 years, Intel stock growth faster. That actually was a driving force for this PC evolution, okay? Computer evolution. So after I joined Intel, about summer, Intel stock price passed IBM. So Intel is a bigger company than IBM. It's fast growing. But after I spent 1 year, Microsoft outpassed Intel. Okay, they are more faster growing. Okay, after I left, and when I was usual by Cisco, much faster than Intel, and Microsoft, Cisco, whatever. And then year 2000, all this stock price go down. Okay, can I give you some good, some interesting history of this stock? Actually, at the time, I had a friend, Korean friend, who also graduated from University of Illinois, Urbana-Champaign, and he spent about 5 years at Samsung for semiconductor business. And Intel was growing too fast, and he moved to Intel, from Samsung to Intel. And his goal was, I just want 2 million, and then I want to retire. Okay? So because of experience, he actually had more stock options than I. Okay? And around the year 2000, his stock value was about 1.8 million. Okay? Because of this growth. He said, he gave me a call. He changed his car to BMW, and he gave me a call. Oh, it's almost time for retire. I'll go back to Korea. Okay? So he came by, and he came by with his BMW, and we switched my car and drive, and so on. And then he was trying to go back, and this IT bubble collapsed. And it was around the year 2000, April or something like that. And he exit. And after your exit, you have to exercise your stock option, because you no longer belong to Intel. Then you have to sell all of your stock. Okay? And you are given 3 months. 3 months. And he cannot sell because of too much price down. So he's waiting. At the last day, 3 months last day, until the last day. And then he exercised. How much he earned the money? $1.8 million to $5,500. Because stock option means you just earn the price difference between your entry and whenever you sell. So if the stock goes up, then you can earn a lot of money. But if your stock goes down, you earn no money. Okay, so that was the. So you don't know. So you should not depend on this. And anyhow, so today's microprocessors, Core i7 is a quad issue superscalar, which means every cycle it can fetch 4 instructions, decode 4 instructions, and execute 4 instructions, and you can retire, write back 4 instructions. Okay? And your smartphone, Galaxy S4, S3, or iPhone, they are usually dual issue superscalar ARM processors. So those are all superscalar processors. We say they exploit instruction level parallelism because every cycle you are not executing a single instruction, you are executing more than one instruction, 2, 3, or 4 instructions. It starts from Pentium. Pentium was 2 issue superscalar. Pentium Pro, Pentium 4 was 3 issue superscalar. Okay, and Itanium is 6 issue superscalar. Okay. And we have studied in-order pipeline, which means in the instruction pipeline, which is fetch, decode, read stage, all the instruction goes through this in-order pipeline in program order. Okay, they can complete out of order, but at the execution unit, but instruction pipeline, they have to go through the pipeline in program order. Okay, but most of high performance processors used for PC, such as Core i7 or i5, they are out of order pipeline. So out of order pipeline, I'll give you simple introduction of out of order pipeline. So after fetch and decode, instead of read state, you send to instruction window, or this is called also reservation station. So these are instruction buffers. You send here, and then you wait for source operand. If both source operands are available, you can issue to the backend execution pipeline, which can be ALU or memory or floating point unit. Right? These are actually out of order pipeline. It's a little more complex. So reservation station means each execution unit has its own buffer. It's called reservation station. So based on if it's integer, you issue to the reservation station for ALU. If it's floating point, you issue to the floating point reservation station. If it's memory operation, you send to the memory operation or reservation station. When you issue from the register file, you can read the available operand. If the operand is available, you can read it and copy here. And then you can eliminate write to read dependence. Because you allocate new storage. You have copied all the available one, if they are ready. And you have also storage for the destination here, so you can eliminate write to write dependence. So there is only true dependence you have to handle, because write to read, write to write dependency is handled by storage in the reservation station. Okay, that's why this write to read and write to write is called force dependent. You eliminate using this register renaming, and then you have this bypass network. So that for true dependence, you can reduce the latency of this delay. Okay, and this is used for Intel, starting from Pentium Pro. They also use out of order pipeline with this kind of reservation station. It's also used by IBM RISC processor, which is PowerPC. Okay, and the original algorithm, this is called Thomas Law algorithm. Thomas Law algorithm is used by IBM 360, which was delivered in 1960s. So this idea is about 50 years old. Okay? So, if you come to graduate school, you want to do some research, you think about new idea, and then it's already done by other people because so many people are working on this field. Okay? Anyhow, this concept is actually I taught at graduate school, not the undergraduate school. So you just know the concept. Okay? That is called out of order pipeline. They use this Thomas law algorithm. And this kind of technique is used for Pentium. So for example, these are examples. Pentium 4, which is three-way superscalar, which means 3 instructions every cycle, fetch, decode, read, execute, and 20-stage pipeline, and it's out of order pipeline. So it has this reservation station and register renaming. MIPS R10000. MIPS R10000 is called Beast, the code name. Intel Itanium processor, the project name was called Merced. So when I joined Intel, they didn't decide the product name. So we called the Merced project. I was working on the Merced project. Merced is a river. So this is United States, okay? This is Yosemite Mountain, California, okay? And this is a river flowing from Yosemite to Pacific Ocean. This is called Merced River. And they use this geographic name for all Intel processor project because they want to confuse AMD because they say 486 or 586, 686, then they know what they are doing. So they change all this code name. So Merced. And so actually when I joined Intel, I had an offer from Silicon Graphics who built this MIPS processor. So I went to Silicon Graphics, which also was in Silicon Valley. Actually, Silicon Graphics is called SGI. Their offer was about $20,000 more than Intel's offer. And they have bigger sign-on bonus. $10,000 more sign-on bonus than Intel. So, and at the time there was a Jurassic Park, which was made by Silicon Graphics Workstation. So that was the fast-growing computer company at the time. But I thought Intel is better because Intel has a brand and the history. SGI is only a few years of history. So I decided to join Intel. And MIPS R10000 was built, the project at the time when I worked on this Merced. So there is another, this is for their workstation processor, high performance. The code name was called Beast. And actually my office mate, on the same advisor, actually he joined this SGI. But the company actually disappeared after about 6 or 7 years, and their stock price went down. That was the peak. So if I joined them, then that should be a mistake. So I made a good decision. So whenever you select your first company, you have to look at their brand, not just salary, okay? You have to look at the brand. So MIPS is a 4-issue superscalar out-of-order pipeline. UltraSpark is a processor built by Sun Microsystem. It's 4-way in-order pipeline. Digital Alpha, this is the fastest microprocessor. 21264 is 4-way out-of-order pipeline. So, 알겠죠? Let's look at the example for superscalar pipeline. Assume 2-way superscalar processor with following pipeline. So you have one ALU that can do addition or subtraction, and the operational latency is 1 cycle. So it's not pipeline because it takes 1 cycle. Okay? And you have one multiply divider, and this multiply division operation takes 4 cycles. And you have 2 memory pipelines. Even though you haven't studied cache, let's Assume that you know your cache. And you have 2 levels of cache. If you hit the first level, it takes 1 cycle. If you miss, it takes 4 cycles. Because you have to go to second level cache. Okay? And show the pipeline diagram for the following code. Assuming full bypass network. Okay? And because these are 2A superscalar, you can actually fetch and execute 2 instructions at a time. Okay? So first 2 load. The first one is hit first level cache hit, but the second load is a miss. Okay? Then first one it takes fetch, decode, read, execute, write back. Second one will take error, miss, and it goes to L2, 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 and write back. It takes 4 cycles. Okay? Because miss means cache is a small, fast memory between processor and memory. Okay? And cache is initially empty, but once you bring in the new instruction or data, you do not throw it away, you store into the cache. When you access the memory next time, sometimes you can find the instructional address from the cache because you access the same instruction or same data again and again. It's called temporal locality. Okay? You think about instruction of loop, you execute the same instruction again and again, right? Data is also the same. So if you hit the cache, you don't have to go to memory, you can get the data from the cache. Okay, and then you have this multiply and add instruction. Multiply is trying to read R1 and R2. R1 can be bypassed directly, but R2 is available only here because you miss R1 cache. Okay, R2 is bypassed, and multiply takes 4 cycles and write back. Okay, and addition is reading R1 and R2, and it's bypassed, and it can complete earlier, right? Because addition is simpler than multiplication. And subtract, okay, R3, R4. So they have dependence between 2 instructions. So you can read R3 here. R4 is already available, so bypass and complete subtract. Addition is reading R4, so you bypass here, complete earlier. Okay, and store is reading R5, so you bypass and store, and this is reading R4, so you bypass and store and so on. You don't have to bypass because you complete earlier, so you read from register file and write back. So you can write back 2 instructions, right? 2 instructions every cycle because this is 2 issue superscalar. Understood? So you can think of this pipeline diagram for superscalar processor as well. Okay? Okay, so exercise. Okay, right after read dependence violation cannot happen in the in-order pipeline. We already discussed this issue. What is pipeline interlock? Stack top. Still no one is sleeping, so you are still on the stack top. What is pipeline interlock?
What is HW?
Hardware. So pipeline interlock means you have to check read after write, write after write, or write after read dependence, right? Usually for in-order pipeline only read after write and write after write dependence. And you need this register comparators, right? After you check the dependence, if you find the dependence, you have to lock the consumer instruction at the read stage, which is recycling, pipeline store, right? Whenever you detect the dependence, you have to store the pipeline at the read stage, right? Which is called pipeline locking. You are locking the pipeline. It's called pipeline interlock. You check the dependence and locking the pipeline, storing the pipeline, which is called pipeline interlock. Pipeline interlock and data bypass. Pipeline interlock just stop the consumer instruction, right? Because you have to wait for the producer, right? But the data bypass is before the producer exit the pipeline. You can send the data immediately after they produce, and this is called bypass. Okay, so this is somewhat additional function. So a real difference. Interlock means you check the dependency and you lock the pipeline. With bypass means you send your data as soon as it's available so that you can reduce this latency of storage times. Okay? How do the execution pipelines such as floating point affect process performance? So we already discussed. If floating point operation takes more than one cycle, if you have back-to-back floating point instructions, sometimes floating point operation might be busy and you have to you have to generate store because of the structural hazard. The solution is you can pipeline the floating point unit, or you can install additional floating point unit, right? But usually pipelining is cheaper, okay? That's the floating point pipeline. So if you look at the processor specification, they say this floating point unit is pipelined or not pipelined explicitly. And then you know what the meaning, okay? And these are the homework. Homework is due. So next Thursday is actually exam. So homework is due Tuesday following the exam, okay? So about
Why not exam date?
next Tuesday and Thursday. Thursday is what day? It's not in this room, it's 창의관. I don't remember exactly something like this. And it will be announced at the homepage. And my student told me. Okay, so you have to look at the homepage to identify this room for your exam. And exam, you should solve all this exercise from the textbook because at least 50% will come from this textbook exercise. Okay? So do lots of exercise. 뭐라고? What? Yes, the textbook, and there are two textbooks, right? So all the related textbook chapter exercise you have to solve. Okay? Okay, so let's go to a new word, memory. memory.
정리 한번 해주면 안 돼요?
정리?
시험 범위.
시험 범위는 the coverage of the midterm exam is up to pipelining. So this is belongs to the final exam. Okay? Pipelining, until the pipeline, do you have any question? So he said he wants some summary. Do you want me to go through quickly all the materials? Or do you want me to continue?
Continue.
How about continue? Raise your hand. Review. Raise your hand. Review. Review. Okay. Let's start from introduction slides. Okay. So we can view processor from top to down, right? So this is computer, right? You look inside, processors, memory cards, and so on. And these are the memory cards. These are the processor. These are the memory slots. So you put this memory slot into here. It's called DIMM, dual-in memory modules. And this is double data rate because every bus cycle you can send twice. Okay. And this is a processor chip. This example is Pentium 4. And actually, all this logic is you can view them as a NAND gate. NAND gate. Everything is a NAND gate here. Yeah. NAND gates and wires. That's all. Okay, so you can view processors as a collection of NAND gates. NAND gates. Okay, even memory is a NAND gate, right? You have studied NAND gate latches, right? NOR gate latches. It's latches. SRAMs are latches. So this advanced transfer cache. Cache means SRAM. So you have latches, NAND gate latches. Okay. And these are the pipeline, which means fetch, decode, and you have floating point unit. Trace cache is an instruction cache. Another latch, NAND gate latches, and so on. Okay? So NAND gate is a universal gate. So you can, using the NAND gate, you can build AND or NOT everything. And NAND gate, you can use actually 2-input NAND gate. You need 4 transistors. These are CMOS transistors. So you have PMOS and NMOS. NMOS and PMOS transistors. Okay? These are switches. If it's high, you turn on. If it's low, you cut off, switch. This is reverse. Reverse. This is more like a NOT. So using the switch, you can interpret this circuit easily. Okay, because this is a switch, switching logic. And using this NAND gate can be implemented using these polygons. These are physical design. So as I said, 600 designers. About 30 people are micro-architects. And about 50 people are logic designers. These are all working at the logic NAND gate level design. Below you have circuit level design. Below you have physical design. And this is done by mask designers. These are actually contractors, not 요즘 뭐 신의 직장, 뭐 직장이신 나오지 거기 계약직 해가지고 뭐 나오대 공부하느라고 드라마 안 보지. 김혜수가 나오는. There is a drama called Goddess of maybe 직장을 뭐라 컴퍼니. 예, these are made by contractors. And so this shows Intel x86 processor family evolution. Okay, so this actually they interpret the same language x86. So the same program can be portable to any processors, but they are different by their internal design, which we have studied. Their pipelines are different. Their caches are different, their branch predictors are different. Okay, it's called microarchitecture. And 486 is second generation, Pentium is third generation, and Pentium 2, Pentium 3, Pentium Pro, these are fourth generation, same design, same pipeline, same architecture, microarchitecture. This is fifth generation. And these are spec. So spec independent performance evaluation, non-profit organization. All this processor performance is relative to reference machine. Reference machine. Okay, this was used by spec integer 95, but nowadays they use spec 2006. Spec 2006. At the time for spec 95, reference machine's relative performance was 1. So this Pentium 4 is about 80 times faster than reference machine. But spec 2006, reference machine's relative performance is 100. So maybe 1000 means 10 times faster. Okay. Okay. So these are terminology. You have to know what is instruction set architecture, what is CISC, what is RISC, what is word. So you have to understand 32-bit microprocessor means they're integer arithmetic unit. They are doing 32-bit computation. Okay? For 64-bit processor by default, they are doing 64-bit computation. 8-bit processor, they are doing 8-bit computation and so on. So Intel processor is Intel Pentium 4 based on spec 2000. Their relative performance is this, which means this reference machine's relative performance is 100. So this is about 12 times faster in floating point, which is server, and also for integer benchmark. And this shows another performance curve. This is showing Moore's law. So you have exponential performance growth in this time period. After year 2002, it's saturating because of the power issue. And superscalar processor is not scalable, which means even though you add more transistors, your performance does not improve much because it becomes too much more and more complex. You spend too much power, too much energy, but the performance gain is only marginal. So in superscalar, which is instruction level parallelism, from here they emphasize more multi-core or multi-threading, which is called thread level parallelism. So you do not learn a single application, you expect more performance. You have multiple cores and each core learn different programs. And throughput, total system throughput will be increased. This is i7 processor. So using this as a reference machine, this is for spec 2000. Reference machine performance is actually 1. So they change reference machine 1 to 100, something like that. And compared to reference machine, it's about 159 times faster in integer, about 100 times faster in floating point benchmark. And this is 14 stage, 4 issue out of order pipeline. So this is used by A6 chip is used by Intel, Apple i5, I guess. Apple iPhone 5, right? The newest one. And inside they have this chip called A6. So it's SoC. So it has processor, but it has other peripheral circuits. It integrates other circuits into the same chip. It's designed by Apple, manufactured by Samsung. So who won more money? Apple, not Samsung. They use 32 nanometer process, and inside they have this processor core, which is called ARM version 7. This is instruction set architecture based dual core processor. So it's dual core means it has 2 processors inside a single CPU, and it runs at 1.3 gigahertz. And they are actually triple issue superscalar pipeline. So they fetch, decode 3 instructions every cycle. Okay? Okay, so this equation is quite important. You have to look at 3 components to determine the performance. The first factor is program size. The second factor is CPI or IPC. third factor is clock cycle time or clock speed. So this is execution time. To improve performance, you have to decrease execution time, which means you have to decrease program size, decrease CPI, or decrease clock cycle time, or you have to decrease program size, increase IPC, increase clock speed. Okay? You cannot just compare the clock speed alone. You have to look at IPC. And if you compare Intel processor with ARM processor, you have to look at program size also. In terms of program size, which one is better? CISC is better because programs are more compact. Okay. Okay. Does this help you, or should I continue the memory? 괜찮아? 도움되나?
네.
돼? 새로워? Okay. Okay, let's look at the instruction set architecture. Okay, you have reviewed this. This is internal process of compilation. You have lexical analysis, syntax analysis, and intermediate code generation. This is more like a machine-independent machine instruction. Right? So from the source program, you generate a sequence of token by lexical analyzer, which means you see the identifier, constant, or keyword, or something like that, or brace operator, some, and so on. And then syntax analyzer build a tree, which means this is identifier can become a subject, okay? Verb and object. This can make a sentence, okay? And program might be a collection of sentence or collection of statement. So you build a tree. So intermediate code generator, this, you can scan this tree from bottom up or top down, and based on this scan, you can generate the intermediate code. Okay? And then code optimization, you change the sequence of instruction, or you remove unnecessary instruction and so on, so that the result code can run faster on the machine. Okay, you do lots of analysis, and then target code generation. And this is also front end and back end. You can divide like this. So what are the machine states? Registers and memory. So computer or processor, as a result of executing instruction, you update the machine state. You change either register, you change either memory. Okay? So we have reviewed machine instructions, which I assume you now familiar somehow. Okay? And instructions can be classified into arithmetic, data transfer, and control transfer, which is a branch. And for 32-bit instruction, you have to encode this information into an instruction, binary instruction, and you can divide this into opcode and operand, which are the data, and these are the operation, what to do. Okay? And addressing means in here, you have to specify either data address, sometimes instruction address for branch instruction, and those are how you address. Okay? These are the encoding examples, and these are the program address space, which is also virtual address space. So instruction goes here, and global variable, state variable locate here. So actual.exe file contains only this. Okay? If you double click from disk, you load into this virtual address space. And at the same time, once you execute, these are built at runtime dynamically. Whenever you call the function, you allocate stack frame. Whenever you call malloc, you allocate the data as much as you want. And you can deallocate using the free. Right? These are called heap. Okay? And we have seen these examples. So you have to do some assembly programming. In the exam, there will be assembly language programming. Okay? So I give you some C code, do this in a MIPS assembly language. Okay? You don't have to know exact MIPS instruction, but you have to encode. Right?
If the code table, this code table.
I don't ask you to encode in binary. I just ask you symbolic machine language, assembly language. So you should know this level of language instruction. Okay? Whatever. The question is not to memorize the details of MIPS instruction. You have to know the programming skills. So even though your instruction is a little bit, there is an error, it's okay. Okay? But you have to program like this. I am looking at the algorithm or your mechanics of your programming. Okay? So there will be some exam questions that you have to program. And then we have studied linking, which is assembling different pieces of translated code, which is a relocatable object file. You group together and make a single executable file. Right? That's called linking. So you do this separate compilation because you don't. If you have a single program file, if you want to change, then you have to recompile everything. If you want to share, you have to copy everything, which might be too big. So you decompose into different pieces and you compile separately and generate this relocatable object file. But to produce actual executable, you have to combine them all. And this is called linking. So here, if you have this example, the linker should find out which are the symbols they have to relocate, right? There are some symbols and so on. Okay, some of them are symbols defined locally, some of them are defined externally. Right? There are definitions, there are references. And when you link them together, then each definition should find each reference should find exact definition. Right? And you have to identify which symbol you need to relocate. And to do that, you need this linker rules, a strong symbol or weak symbol. Right? And there should be no ambiguity, otherwise it can cause some problems. Okay? And so linking is generally you move this code section together and merge into a single code section. You move data section together and merge them a single data section, and so on. Okay? Since you mapped into a virtual address space, their address becomes definite, right? Absolute in the executable file. So you can change your reference to absolute location by the linking. So in this code example, these are symbols. They should be relocated. And they use PC relative addressing because this is instruction address. So they put question mark here. So red mark means it's like question mark. Okay? So these are also question mark. You have to relocate. And this is for data address. So you put 0, this question mark. Okay? And also in the data section, they have this address, which they don't know yet. So you put question mark. After you merge them together, and then they can identify the address. So they fix all this question mark into absolute position, absolute address. Okay? And you can do this linking as compile time And you can also do that at runtime. Okay? At runtime, because you don't want to duplicate the same code in different process, which is the current running program. You don't want to duplicate the same code in the disk file also. So in that case, you should use as a shared library or dynamic library, and you can share at runtime. Okay, there is only a single copy in physical memory. It's shared by multiple process. Okay, so we have static linking process and dynamic linking process. And we have also studied library, which is a code written by other people to facilitate or to help you to program quickly. Okay, it's a set of relocatable object files. And if you include this library header files, and you can use any of the functions defined in the library. And the linker will select only those relocatable object files that are actually called by your program. You don't have to copy everything, right? Okay. Okay, linking. What else we have studied? Oh, and then pipeline. Pipeline, I don't have to go through, right? Since we have just finished this pipeline subject. Any questions so far?
출문제요. 출문제 같은 거.
No. No solution. What?
컴퓨터 알쓰레기
ID?
컴퓨터 알쓰레기
컴퓨터 뭐?
We don't read it.
아, 컴퓨터 어리스메리? 그랬네, 빵원. Arithmetic is simple, two's complement, you know, right? So we can go to multiplication is like where this is hand calculation, right? So you put multiplicand in M register, you put your multiplier in Q register, and by looking at Q0, you can add this multiplicand to your accumulator while do nothing, step by step. And every time you do shift right so that you examine the next digit. Okay? And you can do this binary multiplication simply, right? So you need just one adder and 3 register and some control logic. You can implement adder, also subtractor and multiplier, and even divider, right? So this is tells you how they can do this multiplication. For signed multiplication, there is an algorithm called Booth algorithm. They look at 2 bits at a time instead of single bit. Then sometimes you can skip, right? So if it's 0, 0 or 1, 1, you do nothing. If 0, 1, you add. If it's 1, 0, you subtract. Okay? So if I give you some numbers, do the Booth algorithm procedure, then you draw these steps, okay? For some negative numbers, okay? Division is reverse, inverse procedure of multiplication. You put dividend in Q register, you put divisor in M register, and you reset A, and you do shift left, and you examine accumulator. If you do subtraction, and then you check less than 0 or not, right? If less than 0, you add back. You cannot divide, right? You cannot subtract. If it's greater than or equal to 0, you can subtract. So you could put quotient. Right? With this step for n iterations. Okay, this is for unsigned division, and finally quotient in Q and remainder in A. And sign division is a little bit complex. Floating point numbers, I hope you can remember, right? So, not long ago we have reviewed this. So, you have three components: sine, exponent, and mantissa. Using the sine, exponent, and mantissa, we can express all these floating point numbers. Okay? And algorithm looks complex, but if you follow, it's quite simple. Right? 또 없죠? 자, 여기까지 합시다.